Normally, there's a hormone that when you eat, it tells you when you're full. You become resistant to this hormone when you eat fructose.
Dr. Rick Johnson, I cannot tell you how thrilled I am to welcome you to The Better Show. Welcome.
Thank you. It's just a delight to be on your show.
And I have to say, this conversation is quite serendipitous. I was interviewing Dr. David Perlmutter, who you know very well. And towards the end of that conversation, I said, well, you know, I've had Dr. Robert Lustig on the show. I've had you. I said, the person who's going to finish off this triangle of sugar and, you know, uric acid and fructose is Rick Johnson. And he's like, oh, well, I'm just going to send an email and introduce you. And literally within 5 minutes of finishing the recording, you know, we said our goodbyes. There was an email in my inbox introducing you, and here we are. So I'm very, very excited to be having this conversation with you.
Well, it's a real pleasure to be on your show. Those are both two wonderful scientists, Dr. Lustig and Dr. Perlmutter.
Yes, and they both had a lot to say about fructose, and I suspect, and sugar in general, and I suspect that you will as well. And I thought that that might be a good place for us to start. We're discussing your new book, Why Nature Wants Us to Be Fat, which is such an incredible title. Yes, there it is. Nature Wants Us to Be Fat. So I thought we might start with some mechanisms. And as we were talking about in the pre-show, you know, I love to geek out on mechanisms and why and enzymes and this and that. But we also want to, you know, keep our listeners in mind and give them some of the actionable items around why this matters. But I think before we do that, it's useful for there to be a base level of understanding in terms of the structural and functional differences, let's say, between glucose, which, you know, Dr. Lustig has coined, and I love the molecule of life, and fructose. So, you know, we talk a lot about glucose on the show. I talk about a lot about glucose in general as it relates to female health. And I would love for you to, just for an explanation for my audience, structure of glucose, structure of fructose, and then the functionality difference between them.
Okay, well, when we get to carbohydrates, there's two major sugars that are important. And one is glucose, and it's a 6-carbon sugar. It's a very small molecule. And it is the molecule of life. Dr. Lustig is right. It is the energy-producing molecule that our bodies use as its major carbohydrate fuel. And so we have a fair amount of glucose in our blood, and it goes into our cells and is converted to energy. And it really is the standard carbohydrate fuel that we get. So like when you eat bread, that's starch, and starch is many, many glucose molecules put together, and they've broken down, and then and the glucose is our fuel. And if the glucose levels are too low, we get hypoglycemic, and we get agitated and confused and lightheaded, sweating. And if our glucose levels are high, we get hyperglycemia, which is, if it's persistent, is called diabetes. And if it's mild, it's called insulin resistance. And so glucose is like the major fuel. Now there's another carbohydrate that's the same size, you know, practically almost very, very similar in structure. And that carbohydrate is fructose. And people have thought of fructose as really something that we just metabolize. It's just another carbohydrate. And but fructose is the main carbohydrate like in fruit, and it's why fruit is so sweet. It's also combined with glucose to form sugar. So sugar is really glucose and fructose together. And the fructose is sweeter than the glucose. And the reason we like sugar is we like that sweet taste. And glucose is sweet, but just much less. And then people realized that, you know, this combination of glucose and fructose really tastes good. And so they made this syrup called high fructose corn syrup. in which they add a little bit more fructose to the glucose to make it a ratio of 55-45 instead of the 1-to-1. And that seems to be the taste that people prefer the most in tasting experiments. And so that sweetener got added in the 1970s and has been added. It's added to a lot of foods because it's liquid and it mixes in well. And so about 15% to 20% of our diet comes from these two added sugars, either table sugar, which is glucose and fructose, or from high fructose corn syrup. And some people are eating 25% of their diet from these sugars. Now, when it comes to these sugars, it used to be thought that fructose was just like glucose. It was just another carbohydrate with similar effects. And work largely led by my group back in around 2005 started to realize that fructose actually had major biologic differences from glucose. It tended to make animals want to become very fat, and not just fat, but they would get hungry, and fructose would cause hunger and make the animals search for food. And it actually seems to stimulate fat production as well as insulin resistance, what we call the metabolic syndrome. And when it became very apparent that fructose was distinct from glucose in its ability to cause fat, everyone began to become aware that fructose was a major problem. And Rob Lustig was one of the great leaders early on, championing the fact that fructose in sugar was different from glucose. Our group actually tried to figure out why that was. And it turns out that it's all about energy. So, everything we eat, calories, it's all to help us produce energy. And even the oxygen we breathe is used as to help us make energy. And energy is what really distinguishes what we are. Energy is how we think. Energy is how we act, move, walk, talk. And so the energy in our bodies is really critical to who we are, our biology, how long we're going to live, how much energy we have, And so it turns out that energy is produced in these little energy factories called mitochondria. And they pour out energy in the form of ATP. That's the currency of energy that our body uses. And ATP is a complicated name, but it's adenosine triphosphate, and it's basically a molecule that provides energy by donating phosphates. Anyway, we make this energy called ATP. But there's one other major form of energy, and that's stored energy. And so when you produce energy, you can produce the ATP, or you can store the energy as fat. So fat is a form of stored energy, and ATP is a form of instant energy. You can also release energy as heat, and that's called uncoupling. But we're not going to talk about that for now. But basically, if you think of energy as stored energy or instant energy, glucose is the fuel that wants to make instant energy. And it will store some fat. It will produce some stored energy. But mainly glucose is to provide instant energy. Whereas fructose, it turns out fructose, its main goal is to make stored energy. Its main goal is to make fat. And the way it does that is really clever. And what it does is it acts when you eat fructose. When you eat fructose, you're actually consuming a little bit of energy and while you're from the metabolism. And that sets off a reaction, a unique reaction to fructose that what it tends to do is it tends to produce a thing called oxidative stress. And it does so by producing a substance called uric acid. And that substance quiets the mitochondria, these energy factories that are making energy. And it reduces the energy output from the mitochondria. And by so doing, it reduces the amount of oxygen that's needed because oxygen is used to produce energy. And it creates a low energy level in the cell. And that tells the organism, or it kind of signals that there's an alarm signal going on, because we want to have high energy. And so if you create, even if it's sort of fake, if you take this sugar, fructose, and you eat it, you drop the energy in the cell and you make the animal think that it doesn't have enough energy. So what's it going to do? It wants to store, it's saying, hey, there's danger ahead. We don't have enough energy. I need to eat more. I need to start storing energy. I need to build up my fat stores, because if I get into a situation where there's no food, nothing to eat, I'm going to have to produce the energy from myself. And so what fructose does is it creates this alarm signal, and in so doing, it activates processes to preferentially take the food we eat and store it as fat for the rainy day, as opposed to immediate energy. So fructose tricks us. Fructose is a trickster. It wants to make you feel like you don't have enough energy, and in so doing, gets you to eat more and store more fat. And this is what animals will do. You know, when we kind of figured out this was what was going on, we started looking, and we saw that that a lot of animals, regulate their weight perfectly. They eat more one day, they eat less the next. And actually, there's even some data that humans really were meant to do the same. If you eat more one day, you exercise, you eat less the next day, or you make it up by exercising more. And we're really meant to keep at a regular weight. But if you activate this switch, you eat fructose, you activate this biologic switch that makes you want to gain weight. And that's because you drop the energy in your cell. And when you do that in your cells, and when you do that, you get hungry, and you start foraging for food, and you start activating this process to protect you from a period of food shortage. And so that's how fructose works in the big scheme. We can get into the details if you like.
Always. Always want the details. One of the things I learned from you, which I thought was so fascinating, this was from this current book and your last book as well, I believe it's called The Fat Switch. I have it upstairs, is that when we consume glucose, let's say, there is like a little bit of dip in ATP, but there's almost like a regulatory feedback system to make sure that those ATP levels don't drop. And that's sort of mediated by, a bunch of steps, but like phosphofructokinase. And when we look at fructose, it starts to consume ATP almost in like an unregulated way. And to your point, there's all of these other metabolic knock-on effects, like the animal, let's say, you talk about bears and you talk about camels, and we can talk about them in just a moment. But in terms of some of the metabolic effects for someone listening, like, okay, well, why would I care about how much fructose I'm consuming? The cell is going to start consuming ATP in this unregulated way. And we can talk about the steps, how we get down to AMP, but the animal is going to reduce its metabolism. It's going to reduce its REE, its resting energy expenditure. It's going to get thirsty. And then we're going to start shunting rather than, as you had so eloquently said, we either have this instant energy that glucose is producing, or we have the adipocyte, we have this storage form. So you're basically shunting the pathway away from instant energy, away from producing ATP to consuming it, and to have this sort of lipogenic effect. And I would love for you to expand on, sometimes when you think about, like, why would that be something that we have? Like, why is that a thing? I love to look at things from like an evolutionary perspective. And I think that context here might be important because
yes.
the
So
title
let me
of
talk,
your
So let me talk about two things. One is the big picture stuff of what happens it's like a survival switch in evolution. And we'll just talk about all the things that we identified that fructose does. And then I'll explain the biologic mechanism in more detail.
Yes.
Okay. So it turns out that when you eat fructose, as I mentioned, there's a drop in energy and it signals to the animal that it's in trouble. Now, the interesting part is if you eat fructose, you can actually have plenty of storage fat. You're actually okay. But because it drops the ATP, it tricks the body into thinking that it doesn't have enough fat and it wants to put on more fat. Normally, ATP levels are kept at a very, very regulated level. We have a very, very stable amount of ATP in our cells. And if the ATP level goes down, the fat releases, gets metabolized and produces the ATP we need. So normally our ATP levels are great. But what this thing does is when you eat fructose, it prevents the fat from breaking down while at the same time dropping the ATP. So the body thinks it's not getting enough food, and so it starts eating, you start eating more, and so forth. So the switch, the survival switch, is one where first, if you're going to store fat, you want to be hungry. You want to be hungry even if you're eating food. So it stimulates hunger. It does this by causing a thing called leptin resistance. Normally, there's a hormone that when you eat, it tells you when you're full. And what happens is this hormone you become resistant to this hormone when you eat fructose. Interestingly, overweight people are also resistant to leptin. So this is actually what's seen in people who are overweight. And fructose absolutely causes this. We showed this several ways. Okay, so fructose makes you hungry. Secondly, fructose makes you thirsty. If you think a soft drink is quenching, it's not. If you drink a soft drink, you will stay thirsty. And it's because sugar actually creates thirst. And I won't go into the detail of it yet, but basically it makes you thirsty. So now fructose is making, even though you're eating calories, you're getting hungry and you're getting thirsty. And you got to go search for the food. So it stimulates foraging, and it works on the brain to actually it increases locomotor activity. So that means you start moving around looking for food. You have to search for food. And so it increases your activity to search for food, and it makes your visual cortex, in your brain pick out food easier. And it gives you visual cues where you will, and it gives you it decreases your willpower to say no because it wants you to be able to go into dangerous areas to find food. If you're an animal, you have to go out into areas where maybe there's predators. So it creates a little bit of bravery and aggression to be able to go out there, and you can't deliberate. You can't take your time. You have to move, be looking around and trying to figure out what's going on. And so you have to rapidly process things. And so this stimulates this type of behavior. And you can show it in imaging of the brain. So you get hungry, you get thirsty, you start searching for food. And then in the body, there's a stimulation of fat production, called what we call lipogenesis. And there's also a blocking of fat, the burning of fat. So you can't produce the energy from the fat you have. Instead, you're putting more fat in. And at the same time, you become insulin resistant. And actually animals do this when they're preparing for hibernation. They do all this survival thing. They forage, they get hungry, because they've triggered the switch. And when you become insulin resistant, what happens is the glucose in our blood, that molecule of life that Rob Lustig calls, and it really is, it's our main fuel. That's the main fuel for the brain. And if the body thinks that it's in trouble, it wants to keep the glucose available for the brain. And so it does that by preventing the glucose from getting into the muscle. And so it causes insulin resistance. And insulin is required to move glucose into muscle. And so when you become insulin resistant, there's less usage of glucose by the muscle. And so there's more in the blood. And the brain doesn't require insulin as much. And so it can get its share more than its share of glucose, which is important because you want the brain to get that glucose so that you can be thinking. If you're starving, you don't want to be lightheaded and because you're going to get into trouble. So basically it activates this, it raises your blood pressure because it wants to keep the circulation strong. It induces a little bit of inflammation to help fight off infections. It's really there to heighten your ability to survive. So fructose was meant to be a good thing. It was meant to help animals get through the winter when there's no food around. It was meant to help birds be able to migrate across oceans, go thousands of kilometers, where it would not be able to do normally. So by storing all this fat, it provides this energy that you can get and use when there's no food around. So it was really meant to be something. And we, humans, there was a time in our past where it was really important to be able to store fat too. Food was not always available to us. And there were times and we actually have identified periods of time when there were these severe famines that lasted for not 10 years, but hundreds and thousands of years. And when that happened, we actually had mutations occur that allowed us to be more sensitive to sugar. And so we have identified 2 of those mutations. And, as a result of that, we are more sensitive to sugar. And we wanted that because we wanted to be able to store the fat during times of famine. So this is the big picture. Now, if you want me to go into the more detail, it's all working through energy. And it's a story about energy. And whenever you eat food, you spend some energy to make energy. So, you get a potato, you have to, digest that potato, and then you have to absorb it, and then you break down the glucose and you generate energy. And that whole process does require some energy to make energy. It's like you give up 1 checker to make 2. To win 2 checkers. It's basically you do spend a little energy to make energy. But in almost all foods, that energy is tightly regulated. So the energy in the cell never goes down. If you start spending too much energy, the whole thing slows down. But the difference is with fructose. Fructose doesn't follow this rule. And fructose, when you eat it, it causes this rapid burn, and then it sets off a special reaction. And that reaction is driven by an enzyme called AMP deaminase. And basically, when you consume ATP, the ATP is broken down to ADP and AMP. And then the AMP and ADP are then reconstituted back to ATP. So ATP gets burned or used, and then it gets rebuilt. It gets remade. And the mitochondria help remake that ATP. So the mitochondria are producing a lot of ATP, but they need to have that AMP to help make ATP. And what fructose does is it removes that AMP. This enzyme called AMP deaminase is a clever enzyme that removes the AMP, so it prevents us from being able to rebuild that energy. And then the AMP gets converted to uric acid, which is an end product. Once you make uric acid, the uric acid can't be remade back to anything. It has to be excreted. But the uric acid turns out to have biologic effects. And what it does is it goes into those mitochondria and it silences the mitochondrial function by causing oxidative stress. And it blocks the Krebs cycle, it blocks fatty acid, the burning of fatty acids. And it really has a whole bunch of effects to suppress the mitochondria. And what happens is, as part of this, the animal reduces its how much energy it's spending. So another part of the survival switch is, while you're foraging, your energy's fine. But as soon as you rest, it drops your energy more than normal. So you become like a couch potato when you're not doing exercise. But if you are running around, you can run around and look for that food. But then afterwards, you kind of have this resting energy expenditure that is below normal. And you can show that when we give fructose to mice. They will increase their activity initially, and then they will actually reduce their net activity. And you can use laser lights, and they just kind of sit. They don't. It's like an abnormal kind of sitting. They just kind of sit. They don't move around. They're like on that couch, but they.
And so many of us can relate to that, right? It's like sometimes we're all just like, man, what a day, right? And you just like kind of sit and you veg out on the couch. And I love everything you're saying. And so if I could summarize it, and correct me if I have oversimplified this, fructose metabolism essentially is stimulating fat storage. So when it goes down, that we have this drop in intracellular phosphate, it goes down this AMP deaminase pathway. The end product is uric acid. This is going to be that couch potato, right? So you're dropping your resting energetic expenditure, and all you want to do is just like rest and recoup and watch, Netflix or something. And then the uric acid, in addition to promoting, let's say, or inhibiting AMP kinase, is going to block energy, is blocking energy production, essentially.
That's right. That's totally correct. And
so let's walk through two examples, if you don't mind, because one of the things I don't want people to take away is, okay, I can't eat any fruit now. Like, because we know fructose occurs in fruit, it occurs in vegetables, but there's like, I want to talk about sort of the velocity in which the body can extract the fructose. So I'll give you sort of two examples, and you can maybe talk to like the order of operations. But let's say I have some vegetables, maybe some dark berries or something. Obviously, there's fructose in there. There's other things. There's fiber. There's other molecules. Like, for example, in apple, we have things like pectin. Is the fructose absorbed? So, like, you consume the fructose, it gets into the stomach, it's in the small intestine. Are we absorbing that? If it's a small fructose bolus, let's say, is it being absorbed in the enterocyte, or is it moving to the liver where we start to get this like lipogenic type of activity?
Yeah. So let's talk about fructose. And so when you initially ingest fructose, like from a fruit or from honey or from a soft drink, the fructose gets into the gut, and then it goes through the gut into the portal vein and then into the liver. Mm-hmm. When it goes through the gut, there's actually a shield. We call it a shield, but there's about 4 or 5 grams of fructose gets inactivated in the gut, and it just gets turned to glucose. And this was done by a work by my friend and collaborator, Josh Rabinowitz. And so when you eat a fruit, like a 4 or 5 gram fruit, that fructose tastes good, so you eat it, but it actually gets inactivated in the intestine, so it does not do anything. Now, when you eat more than 5 grams of fructose, like an apple is like 8 grams, okay, then a little bit of fructose is going to get across into the portal vein, into the liver. And it's in the liver where the fructose, drops the energy. And that triggers, the liver is like the great orchestrating organ. It actually triggers the changes in the brain, in the periphery, in the fat, and exactly how the liver communicates to the brain. We can talk about that later, but It's not totally known yet. But anyway, what we do know is that when you eat a natural fruit, or if you're eating vegetables that have like 2 grams of fructose, don't worry. It's not going to be a problem. The intestine's going to get rid of it. Now, the other thing is the speed with which the fructose gets ingested. So when you eat, if you drink a soft drink, there's like 20, 30 grams of fructose, and you're going to absorb that super fast because you're swallowing it. When people drink so fast. So you get a soft drink, and if it goes down quickly, if you're guzzling it or something, that's a huge, rapid load, and it gets absorbed very quickly. And then the liver gets hit with a high concentration, because not only are you eating a high amount, but you're drinking it in a very short period of time. So the concentration of fructose that hits the liver is high. And it's the concentration that triggers this energy drop. So if the concentration is high, the energy drop is severe. If the concentration is modest, the energy drop is modest. So it's like a dimmer switch. It's not like on or off. It's like there's a dimmer switch. If you eat a little bit of fructose, you activate the switch a little bit. If you eat a huge amount of fructose, it activates it a lot, especially if you eat it fast. So that's why liquid sugar is so much worse than everything else. Fruit juice, which has multiple fruits, and we think, it tastes so good, but it unfortunately can give you a large dose in a short period of time if you down that juice like I do very quickly. Now, if you actually had a soft drink and you sipped it, like you took one sip and then waited 10 minutes and took another sip, the concentration of fructose that got to the liver may never be enough to really activate the switch. And then the soft drink would be like a calorie. It would not activate the switch. But most of us don't have that power.
Nobody can nurse it.
Yeah. Try to get a piece of cake and eat it over 2 hours. Right. It's not going to happen. Right. So it's the speed, and then it's also that you have this shield. Now there's another twist. 2 other twists. And another twist is natural fruit has fiber, as you mentioned. It has potassium. It has vitamin C. It has all these things. And it turns out that when we were studying how this works, believe it or not, vitamin C, remember I told you that the uric acid triggers the changes in the mitochondria by causing oxidative stress. And that triggers the fat production and the shunting of energy. But that vitamin C is an antioxidant. And so when you give vitamin C, it actually silences some of that oxidative stress that is done by the fructose and uric acid. So vitamin C is a countering mechanism, and everyone should take 500 milligrams of vitamin C, okay? It's just really important that we do that, because the vitamin C actually can block some of the features of metabolic syndrome. That's been shown in people as well. Vitamin C is generally an underrated substance that really does block a lot of effects of fructose. And when we get our the fruit in the beginning of the season, when the fruit's just beginning to mature, it usually has a high vitamin C content and a low sugar content. And birds don't want to eat it and animals don't want to eat it because it's low in sugar and high in vitamin C, and it won't help them store fat at all. But as the fruit ripens towards the end of the season, the vitamin C content falls and it gets a little mushy. It's too sweet for us because the fructose content goes up. And oftentimes fruit that's ripe like that, we don't like it when it's real ripe. But the animals love it because they can get a fair amount of sugar and a low amount of vitamin C, so it helps them gain fat easier for the long distance migration or whatever they're going to do. And likewise, by getting riper and the fructose content going up, the seeds are also maturing. So when the animals eat the fruit, the seeds are mature, and then they'll poop it out, and the seeds will be dispersed, and then the plants will like it because now they're going to be more plants. And so, I mean, on plants, whether they like it or not, but evolutionarily,
Right. Makes sense from an evolutionary perspective.
it's a symbiotic type of relationship.
I love that. So let's move a little bit to, we've been talking about exogenous consumption of fructose. I also wanted to discuss endogenous, again, this sort of like, why nature are you doing this to us? But one of the things that you talk about in your book, and I'm moving towards this polyol pathway, is that we have this mechanism in the body that when we are consuming excess glucose as well, that we can now also convert that into fructose and then have all of these this metabolic cascade that we've been discussing. Can you say a little bit more about this endogenous internal production, our own capacity to produce fructose?
Yeah. So, originally when we were studying this, I was studying fructose and I was thinking, oh my God, fructose is the bad guy. It's the one that's driving. It's meant to be a survival factor, but we're eating so much of it because it's in sugar and all this stuff. This is the main guy causing obesity. And I still believe that. But it turns out that in nature, not always can animals find fruit and honey. And there are certain places in the world where there isn't much fruit and honey. And so how do animals store fat there? And it turns out that the body, nature is wise. And so nature figured out a way for us to make fructose. And there's only one way humans can make fructose. There's only one way, and it's from glucose. And it's through a mechanism called the polyol pathway. And it's been known for 100 years that people can make fructose, but it was never thought to be important. But it turns out that it's really important. And we had a series of scientific studies where we did this research, and we discovered that actually you can make a fair amount of fructose in your body, so much that the fructose can make you fat, even though you're not eating sugar. It was sort of disappointing because I wanted to just have one food to blame. But it turns out that high glycemic carbs are your major, are the major guys that do it. And so when you eat potatoes or rice or chips or cereal or bread, oh my God, I love bread. This was so disappointing. But the bread or starch, if you eat a lot of starch, it will be released in our blood. When it's broken down in the liver, it will release glucose. And if the glucose gets released very rapidly, it'll go up in the blood. And we call this high glycemic foods. And you know about them. We all know about them. And this is why some people have continuous glucose monitors, because they want to know which carbs are driving their glucose up. And we know that, a lot of people say, well, that's bad because the glucose stimulates insulin, and insulin makes you store fat. But insulin does make you store fat. But, usually when you eat glucose and the insulin goes up, it's a very transient thing. The insulin comes up and then it goes down. The problem, actually there's not that much activation of fat. But when the glucose goes up, it also triggers the production of fructose. And when that happens, then you start storing, you activate the switch, and you become insulin resistant. Now your insulin levels are high all the time. And then, and now you're storing fat, you're activating this switch. And so high glycemic carbs turn out to activate this switch. And also, salty foods do too, and there are other foods that can activate the switch, really salty foods. That's why French fries are so dangerous, because the salt activates the enzymes that convert the glucose to fructose. So when you eat the French fry, you're getting that starch, and it's making the glucose go up a little bit, but you're also putting salt on it, and that's turning on these enzymes that convert the glucose to fructose. And so now it's just like the magnificent way to make fructose in your body. And then here's a twist too. Once once you've activated the switch, then fat becomes really fattening. So fat is like 9 calories a gram. So if you're holding on, if you're not regulating your weight anymore, so now if you eat the French fries with the grease on it, the grease is actually giving you a lot more calories. So if you don't activate the switch, let's say you're on a low carb diet or your diet, your Estima diet, and if you're on your diet where you're on a low carb diet, now high fat doesn't really make you gain weight as much because you haven't activated the switch, and so you're still regulating your weight. But if you become leptin resistant by activating the switch with a lot of carbs and so forth, then the fat will be additive, and it will make you gain weight a lot more rapidly, because the calories from sugar are only like 4 calories per gram. So you'd have to eat a ton of sugar to gain fat, whereas the high fat is 9 calories per gram. So you'll actually you'll gain weight much more rapidly with fat once you've activated the switch. So the fructose sort of activates the switch, and then the fat is kind of like the fuel that helps you rapidly gain weight.
Yeah, I love that, and thank you for name dropping my program. I appreciate that. That is one of the hallmarks of the Estima diet, is that it is a low carbohydrate diet, and it's meant to help correct some of the metabolic, let's say, derangement that we can accrue over time. And what I wanted to ask you, I have young children who do love French fries, and it doesn't really seem to bother them. Is there a difference? Is there sort of an age-related sensitivity? And we were talking about this in the pre-chat. A lot of women listen to the show, and one of the things I say is, like, if you're 45, you can't eat the same way that you maybe did when you were 25. So can you speak a little bit about if there is any age-related sensitivity to this pathway, to this endogenous production?
Yeah, so there's 2 aspects, and one is specific to women. So the first thing is that when we're growing as children, we actually don't have the survival switch is not really turned on very much. It is turned on when we're eating sugar, but when we're not eating sugar, for example, high glycemic carbs, we don't have much of the polyol pathway initially in us. It has to be induced. And so when you're a kid, and also you can't absorb fructose very well as a kid. So, and that's because most children are being breastfed, and our babies are being breastfed, and nutrition is not as big an issue. Well, it can be a huge issue, but in general, when we're initially born, we do not have much of this polyol pathway present. But the more sugar we eat, the more fruit juices and stuff we eat, it will increase the transporters for fructose, as well as the enzymes to make fructose, and as well as the enzymes to metabolize fructose, so that over time we become more and more sensitive to sugar. So if a 6-year-old is not going to be as sensitive to sugar as a 60-year-old, because initially we don't have the system upregulated. So, for example, we did a study in children, 14-year-olds, where we gave them a dose of fructose, and some of the kids were lean, some were obese, and some were obese with documented fatty liver by biopsy. And when we gave the dose of fructose, the kids that were lean absorbed only about 2/3 of the fructose. Even though they drank it, they only absorbed 2/3 of it. The kids that were overweight absorbed about 80% of it, but still didn't absorb it all. But the kids that were overweight with fatty liver absorbed it all, basically 100%. So it turns out that our ability to absorb sugar increases with the more sugar exposure we have, and possibly genetics, but a lot of it is exposure. So that's one thing. A second thing is that when we're young, we tend to have very healthy energy factories. And if you're 22 years old, you may feel invincible. You can drink your soft drink and run up and down the beach, and they'll make ads with you, and you can feel like you can eat anything you want. And I don't know about you, but when I was 22, I could eat a huge amount of food. I didn't have to think about the type of food. It could be pizza, cake, whatever, and I wouldn't gain weight. And and that's because my mitochondria were so strong that it was very hard to really trigger that big switch. You certainly can do it if you drink a lot of soft drinks, even or a lot of sugar. You can trigger it as a teenager or as a kid, and some kids are doing that for sure. But in general, the healthier your mitochondria are, the harder it is to activate the switch. And this is why, like these super athletes that do the Tour de France and things like that, some of them can drink sugar without really showing much biologic effects because they're just the mitochondria are so strong. But over time, it's going to take a toll. In women, there's another thing, and that is that women tend to have a lower uric acid level than men. And this is especially before menopause. And this lower uric acid level is associated with a slightly less risk for developing diabetes and hypertension, and it's sort of as a protective mechanism. But when you go through menopause and your estrogen levels fall, your uric acid levels will start to go up, and you'll start now having the same kind of risk factors as men. The risk for developing heart disease and obesity and diabetes will increase. And, what can we do about that? Well, the most important thing is to be aware that this happens. And so, and then to be aware that, that uric acid levels are going up. And so that you're going to become more sensitive to these foods and like sugar and high glycemic carbs and so forth. So, and there are natural ways to try to keep your uric acid down, and obviously eating the right foods is probably the most important way. Exercise can actually lower uric acid, and exercise is really a wonderful way to keep your mitochondria strong. And so, but yeah, there is this effect when you go through menopause.
So when you talk about, just coming back to those teenagers that you were talking about, where you had lean, slightly obese, and then obese with confirmed NAFLD, it seems that you can almost like, with the consumption or increased consumption of sugar, almost have like a phasic shift in terms of your sensitivity for activating this pathway. Yes. So the more sugar that you consume, the worse it becomes. And then when it relates, to your point about women with under the influence of estrogen, with this, call it maybe a protective effect, in that it increases uric acid secretion. That kind of comes back to what we were saying, just a moment ago. Like when you're 55, let's say, you can't eat the same way that you did when you were 25, and right. That's one of the reasons why I really love, for women in general, I love there to be. And I've spoken to Dominic D'Agostino about this, for there to be like this therapeutic intervention of a right. low carbohydrate and therefore low, glucose consuming, low insulinergic environment, so that we can start to heal some of these, we can lower or attenuate some of the chronic activation of some of these pathways. And then, for women who are still in their reproductive years, I like to cycle things based on their menstrual cycle, et cetera. Yeah. But yeah.
Yeah, I mean, one of the most important things, which I really haven't focused on, is that the way this switch works, you eat sugar and you get this oxidative stress to the energy factories. And this suppresses the energy produced by the mitochondria and triggers this biologic switch, okay? And so initially when you eat the sugar, you get this suppression of mitochondrial function, but then it will recover, when you're not eating the sugar. And so it's kind of like a temporary. But what happens is that when you continually eat the wrong foods for a long time, this oxidative stress is recurrent to the energy factories, and over time wears the energy factories down, so that you start actually losing some of the energy factories. And so the mitochondrial function goes down. And when that mitochondrial function goes down and becomes permanently low, then you sort of become permanently overweight. And it's like you're trapped at a certain weight. And then if you try to lose weight, you can lose weight by just, reducing your caloric intake, etc. But then you want to go back to that weight. And so you almost kind of get locked in to this higher weight. And there is a way to break it. This is amazing, but it's really true. And the first thing is you want to reduce the foods that cause this switch, like sugar and carbs, and just
breads.
like what you're doing.
Yeah.
And that we actually did a study in people. We found that just reducing the injury allows the mitochondria to recover. And the mitochondrial, you get this thing called biogenesis, where the mitochondria actually start coming back. So just by reducing sugar, you can do that. Another thing you can do is to exercise. And or intermittent fasting is another way. When you remove sugar and all foods, that allows the mitochondria to recover. So intermittent fasting is also great. But another one is exercise. And I really like the exercise because I think that not only does it make you feel good and gives you and it does burn a little bit of calories, but it's not the burning of calories that's important. That is like the least important. What it's doing is it's stimulating the growth of those energy factories, and that is giving you more energy and is going to allow you to lose weight and keep the weight off. And vitamin C is also good for those mitochondria, especially at a dose of about 500 milligrams a day. I would not go to super high doses because you can get kidney stones, and there's some evidence that at real high doses it may block the ability of the mitochondria to regenerate. So it's sort of a controversial area, and I don't think it's proven, but because we don't totally know, I would not go over a gram of vitamin C a day. But 500 milligrams a day for sure works. It's good. That and exercise and intermittent fasting and low-carb diets. And you know what's really great, Stephanie, is that when you do these studies, what you can show is that when we did the science, it becomes apparent that this is why low-carb diets and intermittent fasting work so well, and people kind of discovered these pathways or these diets and approaches because they worked. And here, I'm coming from the science, and suddenly I'm finding, oh my God, this is why the low-carb diets are working so well. This is why, it's important to cut back on salt. This is why, exercise is so good, because it's intervening through this pathway. And so it's like converging of science with what people have discovered from trial and error. And it's just great.
It's a beautiful thing.
Yeah.
When you say exercise, are you referring specifically to resistance training, cardiovascular, and cardiopulmonary work, or is it just like movement in general, like low, steady state, high intensity interval training, or is there?
Yeah, it is a special type of exercise, and it's really what we call zone 2 exercise. So it's really sort of like jogging or biking or where you kind of try to raise your heart rate up a little bit, not to the point where you can't talk. So my friend Inigo San Millan, who's the coach of the Tour de France winner and so forth, and he's like an amazing physiologist. And his whole purpose of to try to make super athletes super is to try to improve their mitochondria. So his whole career has been on how do I improve a person's mitochondria. And his work, as well as others, have shown that what you want to do is you want to do like 30 minutes to like 60 minutes of exercise at one time. So you need to do this like 3 times a week. I mean, maybe you could do three 20-minute, periods in one day. But basically, you need to have it be sustained for a period of time. And what you do is you try to get your heart rate up to the point where the mitochondria are still burning fat and don't really go into the anaerobic phase. And so what as soon as you start building up lactic acid or lactate in your blood, that's when you're doing it too much. And so it's actually mild exercise. We call it zone 2. And the trick is to exercise to the level where you are able to still talk to someone. So if but it's a little bit difficult. So if it's really easy to talk to the person next to you while you're walking, you're not walking fast enough to really trigger this mitochondrial growth. You want to get to a point where you're just having a little trouble talking. And at that level, you are working on your body to make mitochondria. And as you get better, you'll be walking faster and then at that level, you're going to have to get again to that point where it's a little hard to talk. And if that's going on, then you're at the right spot. And you can also measure your lactate, like with a earlobe monitor. And, there are ways to do it if you want to be more specific. But yeah, no, I think that the power of exercise is something that, a lot of us, who are workaholics, we tend often to ignore the importance of exercise. And we think, if I want to be healthy, I just, eat healthy. But exercise really has a major purpose for us, and that's to help keep our mitochondria healthy.
I love what you're saying, and I'm smirking as you're talking because I've had we've done dedicated episodes on Zone 2 training. I've had Dr. Phil Maffetone on talking about how you increase maximum aerobic function, but not by doing like the high intensity interval training where you feel like you're about to die 4 times a week. And that's what, kind of coming back to women, I'll have a lot of women that will come to me in their 40s and say, I don't know what's going wrong. Like I do like 4 spin classes a week or 5 spin classes a week. And I just have this extra belly weight that I can't seem to shake. And I think that part of that is because they are not spending almost any time in zone 2, that they're probably 5 or 6, zone 5 or 6. And it's kind of like the proverbial, like your brain's like, why are we always running away from the tiger? Like, why is this always a life or death situation? And of course, that hypercortisolemic state is going to cause this ectopic fat distribution for women, which tends to be through the belly. But I love zone 2 training. I think that it's hard to, unless you're sort of monitoring it. I think, I like that cue around like, are you able to hold a conversation around it? Because otherwise, it's very easy, even like with running, for, my runners that are listening, very easy to surpass zone 2. You really do need to be monitoring. And Phil had given like, it's like 180 minus your age as kind of like a general,
So Inigo, has coached a lot of champions, and a lot of them are like CrossFit champions, and obviously high intensity exercise is also something that he recommends for these super athletes. But he swears by the fact that zone 2 exercise is actually great for even if you're a super athlete. And, you want to optimize your mitochondria because ultimately it's energy that is the key, to be a super athlete, to be a healthy person, to have the energy you want to do, to be able to think. And even, in the brain, it turns out that ATP levels, maintaining good energy levels in the brain is probably the best way to avoid dementia. And dementia really is turning out to be an energy disorder as well. And the problem, like with Alzheimer's, is that the brain cells do not make enough ATP, and that they have a problem, burning glucose. They have a problem with their mitochondria, and for years it was thought that Alzheimer's disease is this disease caused by amyloid plaques, and all we have to do is prevent those amyloid plaques, and we can prevent Alzheimer's. But that's the late stage of Alzheimer's. And if you go back to what initiates it, you'll see that the earliest stages are insulin resistance in the brain and mitochondrial problems. And it's now been discovered that people with Alzheimer's have high fructose levels in their brain, and they have evidence of that AMP deaminase and low ATP levels. And the whole story fits for it being a problem of producing fructose in the brain. And, I've written about this, and it needs to really be tested better, but the data is there. And you can, and the foods that tend to be associated with increased Alzheimer's risk, like high glycemic carbs and sugar and the salty foods, are all foods that either have fructose in them or which stimulate the body to produce fructose. So my belief is that what you're promoting, your diet and exercise and this whole approach is actually not just helping people stay healthy and look better and feel better, but it actually is going to have a major benefit downstream by keeping the brain functioning well and reducing the risk for the development of dementia.
And that's, I was saying to you in the pre-chat, that's kind of where I've always had just a love affair in terms of like brain metabolism and, obviously trained as a chiropractor, so very much into the neuromusculoskeletal sort of system. But I've always been fascinated with functional neurology and how we can actually change the brain's perception and output based on modifications like what we're talking about. And I wondered if you can, I know you mentioned it briefly, but I would just like to maybe come back to it if you have anything. I wanted to give you the opportunity to maybe talk a little bit more about this liver brain connection. Like we often talk about the hypothalamic pituitary adrenal, the brain ovarian axis. Is what we're talking about with this state of, a hyperfructose state, let's say, either through exogenous consumption or endogenously producing it via the polyol pathway. Is this also contributing to, we talked about leptin resistance, and one of the things, of course, that we know in terms of the effects that leptin has on the brain is that it downregulates BDNF, brain-derived neurotrophic factor, which is like, I like to call it like miracle grow for the brain, right? It's like the little thing that you sprinkle. It's like the little chia pet, and like you sprinkle it, and then you have the thing growing. And I'm totally dating myself with that chia pet reference. But anyway, so we downregulates BDNF. And then the other thing, of course, that it attenuates is this dendritic, this like synaptic, like the neuron's ability to sort of grow and make other connections. Do you think either through research that you might be exploring or just hypothetically putting together all of the science, that this hyperfructose state is also now causing some of the cognitive impairments, even like the subjective cognitive impairments that we might see, like, you walk into a room and you're like, why am I here? Or where did I put my phone? Like that early stage all the way up to some of the, the tau tangles and the beta, the amyloid beta plaques.
Yeah, so it turns out that when you give sugar to an animal, they'll actually develop problems, going through a maze. And there's many studies that show that sugar intake given, to like mice and rats can impair their cognitive function. I mean, many, many papers. And it's also been shown that this is associated with fructose production in the brain, and that the fructose metabolism is associated with alterations in BDNF, that your brain neurologic growth factors, but also with mitochondrial problems, with cerebral insulin resistance. Now, this is really kind of I know you like evolutionary mechanisms. So it turns out that when you activate this switch, the biologic switch, it causes insulin resistance in this muscle, which allows more glucose to go to the brain. But there's parts of the brain that actually require insulin as well. And so one is the recent memory centers, like what we call the hippocampus. That's where your recent memory is. And what that turns out that glucose to get into the hippocampus actually it requires insulin. And when you eat fructose, you're actually causing insulin resistance to the brain, to the sites where insulin is needed. So a lot of the brain still can take glucose up, but the areas like the hippocampus show less glucose uptake when you eat fructose. And that's because it's causing insulin resistance in the brain. And what happens is it's affecting the areas of the brain that control willpower and also memory. So, that actually is a desirable thing if you're going to go into a dangerous area. If you're going to forage into a dangerous area where there could be predators, you don't want to have a vivid memory of that lion from the day before. So if you can block that recent memory a little bit, it's good. You don't want to have the rational. You don't want to be able to rationalize and say, okay, look, there's a lion in there. I don't want to go in there. And so but it reduces the willpower, especially for the desire for food. And they've actually shown that when you give fructose, you decrease your cortical brain activity, and it translates into you're being willing to give up money for food, for like a cake. It's actually a test they give people, a psychological test to see how much you crave food. And when you give fructose, you trigger this, and it's associated with a reduction in willpower. And that's right from reducing that insulin.
Is that through the dopaminergic
area.
systems, or is that through the dopamine, like the dopamine receptors are
no,
regulated?
that part is not. It's directly linked with the dopamine center, and there's some people showing that the willpower is linked, and so they're probably working on the midbrain and the dopamine as well. Actually, there's evidence that uric acid can increase dopamine levels, for example. So probably is, you're probably right, but when I was saying it's not, I was referring to the activity in the cerebral cortex. So that goes down so that you have less willpower, and that allows you to forage more effectively because you want to be able to search for food and be able to to go against reason, as we say, because of how desperate you are. So it turns out that this foraging response actually wanted to create insulin resistance, but if you're doing that recurrently and constantly, then the hippocampus is not getting enough glucose, it's not getting enough blood supply, and over time it starts to shrink and your memory starts to get bad initially for recent memory, then later for other things as well. And so I believe that Alzheimer's disease is truly an over activation of a foraging response. It's a hyperactive foraging response that has been prolonged so long that it's actually leading to brain damage from low energy levels, chronic low energy levels. And then that triggers the amyloid plaque and the inflammatory response and the tau protein accumulation and all these other things that are associated with Alzheimer's. So yes, and exactly how the liver triggers the brain, it seems like there's a mechanism that leads to the brain to start making fructose, and some thought is that it's from the uric acid. There's some data suggesting that uric acid can cross into the blood-brain barrier. But there may be other mechanisms that we don't totally know yet. It's really a great area for research.
All right. Well, when you have the answer to that, you please promise to come back on, and we'll have a secondary conversation about it. Let's jump to salt, just because I think it's an important topic as well. Kind of rounding out this fructose. We've sort of been dabbling a little bit in it, but let's talk first about salt and blood pressure. One of the things that I've learned from your work really is if I do have a client that has hypertension, one of the first things that I look at is how much fructose they're consuming.
Yes.
So I would love for you to talk about salt in and of itself, because we were all taught in school that, salt is going to increase, of course, the salt concentration in the blood, thereby resulting in hypertension. And I have a lot of questions running a ketogenic diet around electrolyte supplementation. So in a low carbohydrate environment, of course, you're using glycogen, which is stored with, 1 mole of glycogen, 1 molecule of glycogen usually stored with like 3 to 4 molecules, let's say, of water in most people. So as you're utilizing those glycogen stores, as you're in a carbohydrate restricted environment, one of my recommendations is usually to supplement with electrolytes like Na, like sodium, potassium.
Totally understandable.
So let's talk about
let me take you through this. So it's a little bit of a winding story, but let's just begin by saying, that it's been known for a couple hundred years that salt is important in blood pressure, and it was discovered in the early 1900s that if you had high blood pressure and you went on a salt restriction, that you could lower blood pressure to some extent. And so, and then this started the use of diuretics to help get rid of salt as a treatment of high blood pressure. And the question was, why is salt important? Well, how is it working? And it was thought that the problem is that the kidneys in people with high blood pressure can't get rid of salt very well. And so they retain the salt, and then the salt is supposed to kind of cause, through different mechanisms, a rise in blood pressure. So it turns out that this is kind of the classic. Many people can handle salt fairly well when they're young, especially when they're young. But as we get older, we tend to become more salt sensitive to the effects of salt on blood pressure. So if you give a load of salt to a 60-year-old, it's going to raise blood pressure probably. But if you give a load of salt to a 20-year-old, you may see a transient rise in blood pressure, but it doesn't stay high. It's only for like an hour or so. So a lot of people then start saying, well, maybe salt, perhaps the medical field is over-calling salt, and we probably should not have to restrict salt as much as people are saying. And so, the Institute of Medicine came out and said, well, actually, very low salt diets are bad and very high salt diets are bad. We should be eating about 4 to 5 grams of salt a day. But the average person's eating 10 to 12 grams of salt a day. Okay, so that's sort of where the medical field is right now. But it turns out that salt has another twist, and it links it with sugar. And to understand this, we're going to go back to this foraging response and storing fat. And it turns out that when you store fat, you're using it to store calories, but you also are using it to store water. And this is sort of interesting. Fat doesn't actually hold water, but when you burn fat, you produce water. And so when you burn fat, you produce carbon dioxide and water. So a gram of fat will produce like a gram of water or so. And so it turns out that some animals are storing fat as a source of water, not just as a source of calories. So if you're like a whale and you have all this fat on you and you're swimming in the ocean, you don't actually drink the seawater. You don't like the high salt content in seawater. So you get your fresh water from eating the crustaceans and fish you eat, but you also, the whale will get some of its water from its fat. So maybe 1/3 of the water it gets from burning the fat. And the same is true with the camel. The camel burns the fat in its hump when it needs water. And many animals use fat as a source of water. So it turns out that that fat is a survival mechanism that helps animals to protect them from dehydration. And so it turns out that dehydration is a mechanism for turning on fructose. And because by so doing, it helps store fat. So mild dehydration turns out to be a major way to stimulate the polyol pathway. And it turns out that most people who are overweight are dehydrated. And when I mean dehydrated, they're not drinking enough water. But the other way you can get dehydrated, when you get classically dehydration is losing water, like diarrhea or sweating. But you can also become dehydrated by eating salt, because when you eat salt, the salt concentration goes up in your blood, and that is the same biologic response that happens when you lose water. So if you lose water, salt concentration goes up in your blood. And if you eat salt, salt concentration goes up in your blood. And when the salt concentration goes up, it makes the animal feel it does not have enough water, so it feels dehydrated. And so what that does then is the animal gets thirsty and starts to drink water. But it turns out that it also activates fructose. And so fructose is turned on by salty foods. And so if you give salty foods to animals, they'll start making fructose and they'll become fat over time. So eating a lot of salt, which is very common with people who are overweight, is that they're eating a lot of salty foods in addition to sugary foods. But the salty foods is another cause of obesity, and drinking water can block that and can prevent the fructose production and can prevent the development of obesity. So when we gave animals sugar, for example, and if we give them water with it, we can actually slow down the development of obesity by hydration. So water is an unrecognized, absolutely wonderful antidote for obesity, and drinking 6 to 8 glasses of water a day is not a myth. It actually is based on very strong science. It's something everyone should do. Everyone should drink a glass of water with each meal. Drink a glass of water, 1 or 2 during the day. Now, you can overdrink water. There's a thing called water intoxication. And you do have to be careful that you don't drink gallons and gallons, because you can get into trouble drinking a lot of water. And that's especially true for marathon runners and for if you just had surgery. So during that time, you can become a little bit more prone to water intoxication. So you have to be a little careful. But the data is out there. Water is good. People who are overweight tend to be eating a lot of salt. Now then it gets to okay, so if water is good and salt is not so good, what about when you go on a low-carb diet? And the truth is that when you go on a low-carb diet, you're going to start burning the fat in your body. The fat is going to disappear. The glycogen is going to disappear. And as that happens, your body's going to be releasing water. And it's well known that when you go on a low-carb diet during the first week, you're going to be peeing a lot of water. And so there is a concern that you might be getting dehydrated. I think drinking water is excellent, and even some salt is fine. Now, why would salt be, if I told you salt makes fructose, then why would seem to be counterintuitive to give salt on a low-carb diet. But remember, the way salt makes fructose is to make it from glucose. So if you're not eating much glucose, if you're on a low-carb diet, yes, you do make glucose from proteins and fat, but very little. You just make sort of enough to get by. So what happens is when you are on a low-carb diet, a high salt intake is not going to cause obesity because you don't have the glucose to turn to fructose. So the salt turns on the enzyme that makes the glucose go to fructose. So you'll make a little bit of fructose, I'm sure, but not very much. Now, if you take salt with a lot of high glycemic carbs, now you're giving the thing to turn on the enzyme and the fuel to convert the glucose, the glucose, which will then be converted to fructose. So I hope that helps.
No, it does. I'm so happy that you said that, because that's one of the big questions that comes from this discussion around salt and fructose production, is that it's really about the concentration of salt that we're concerned with. So if you have, let's say, even if you have just a glass of water with a pinch of salt, with the consumption of the water, you're still keeping the salt concentration ubiquitous. If you're having some salt with water versus just something very salty, like maybe like a pretzel or something. If you just
we actually did that study. So what we did is we gave soup to people. Okay, and the great thing about soups is you can hide the amount of salt in it fairly easily. You get a creamy soup, you can put a lot of salt, and people don't realize exactly how salty it is. So we could make a salty soup, and we gave it to people, and it made their salt concentration go up in their blood right away. And believe it or not, within 30 minutes, their blood pressure shot up. And and we could also show that they activated the switch. And then we repeated the study, where we gave the same amount of soup to people, but we supplemented it with water. And we did 2 doses of water. And we found that if we gave a lot of water that prevented the salt concentration from going up in the blood, then the blood pressure didn't go up at all and the switch wasn't turned on. So the switch is turned on when the salt concentration goes up. Basically, when you get thirsty, if you're eating salty food and you're thirsty, you've activated the switch. So the trick is to drink water with salty food so that you never get thirsty. And if you do that, then the switch isn't going to be active. So drink a glass of water before you eat the pretzels, and you'll probably be fairly safe. But if you wait till you're thirsty and then drink the water, well, you've activated the switch, and now you're going to try to turn it off. So
right. And just to round out, this conversation around water, it's, when the brain becomes dehydrated, you activate this, there's a stress response. There's this hypercortisolemic state. Like the brain's like, I need water, to your point around, we will conserve glucose for the brain by making the muscles insulin resistant. The brain needs a certain amount of water as well. And so kind of coming back to this conversation around weight loss and metabolic health, or fat loss, I should say more accurately, drinking a certain amount of water, the 6 to 8, I think is a very palatable amount for most people. I think is also going to help with their, if they have weight loss goals where they want to be reducing their total adiposity. I think that's also an important consideration as well, because you won't lose weight in a dehydrated state.
Absolutely correct. That is so true.
Well,
so did you discover that yourself? Just that that was this something that you observed, that if a person's mildly dehydrated, that it's hard for them to lose weight?
It is always the case. I would say at a run rate of 100%.
I think that is a wonderful observation, and it's 100% consistent with the science.
Yeah. I have to say, this has been, I'm just looking at the time, I cannot believe we've been talking for 90 minutes. I want to respect your time, and you're such a wealth of information, well-researched. Of course, you have so much, contribution to our understanding of metabolic health and how to get there and where things can go awry. I want to thank you so much for your time. It's been just a pleasure. I don't know about you, but I want to know how to live forever and look great doing it. All you got to do to figure out how is click the link right here.
1 in 3 adults is obese, not just overweight, but obese. 8 years from now, that it'll be 50%. 50% of adults in North America obese.